Okay, the second colligative property, which is boiling point elevation. All right, you know that the vapor pressure is lowered when you add a non-volatile solute. That means fewer of the solvent molecules can evaporate. So you need more kinetic energy to make more of the solute particles evaporate to finally get the vapor pressure of the solution the same as the vapor pressure of the atmosphere. The way that we are going to calculate how much the boiling point is elevated, and by the way, the boiling point is always elevated when you add a non-volatile solute. The change in the boiling point temperature is equal to Kb, which is the mole boiling point elevation constant. Please be aware that you look to the solvent to find the boiling point constant. The boiling point constant belongs to the solvent. I is the Van't Hoff factor of the solute. Remember, the Van't Hoff factor of the solute tells you how many pieces the solute breaks into. That value is 1 for anything that is not an ionic salt. An ionic salt, the Van't Hoff factor is equal to the number of ions in solution. Therefore, we saw that sodium sulfate has a Van't Hoff factor of 3. Potassium permanganate would have a Van't Hoff factor of 2. Breaks apart into the permanganate ion and the potassium ion. All right. M is the concentration in molality of the solute. You remember molality is the moles of the solute divided by the kilograms of the solvent.
What does that say? How many, the
Pieces. So delta T is the change in temperature. This change in temperature gives you the boiling point of the solution. The boiling point of the solution is always higher than the pure solvent. So to find the boiling point of the solution, you take the boiling point of the pure solvent and add the change in temperature that you have calculated due to the addition of the non-volatile solute being added. You know what, I forgot to include 2 practice problems just on boiling point elevation and freezing point depression, so we're going to jump to the homework and do 2 of those. Let me get the freezing point depression done first.
We already have
Hang on.
You're the best.
Yeah, it's 1 problem and it's the easy one. Freezing point depression. None of this is worthy of taking time here in class. Please read this because it is fodder for the test. But what I want you to get out of this is the freezing point is always depressed. The freezing point always goes down when a non-volatile solute is added. Okay. And we can calculate that with a equation that's really similar to the change in boiling point. The change that of the freezing point when you add a non-volatile solute is equal to the non-volatile solute. The mole freezing point depression constant, which belongs to the solvent, the Van't Hoff factor of the solution, and the molality of the solute. To find the freezing point of the solution, that will always be higher or lower than the pure solvent?
Lower.
Lower. You take the pure solvent and you subtract the change in temperature. This is the depression of the freezing point due to the addition of the non-volatile solute. Okay, I'll do 1 and then you do 1. Let's talk about problem number 1 on today's homework, the colligative properties. Worksheet. Okay. What's the freezing point and boiling point of a solution prepared by dissolving 1 pound, which is 454 grams, of sugar C12H22O11 in 500 grams of water? Well, let's start out with what we know. Let's do the freezing point first. What is the freezing point of pure water? 0 degrees C. You need to know what the molal freezing point constant is of water. It's 1.86 degrees C per molal. That was given somewhere else in this worksheet. You need to know what else? How about a formula? The change in the freezing point due to the addition of the solute, which is sugar, is equal to the freezing point constant of the water times the molality of the sugar times the Van Hoff factor of the sugar. All right, so we got the Kf of the water. What's the Van Hoff factor of sugar? 1. Okay, so how did you know that? It's not an ionic compound. So now I think I need to find the molality, which is equal to the moles of solute over the kilograms of solvent. I do know the kilograms of my solvent, the water, is 0.5 kilograms. I need to know the number of moles of solute. The number of moles of solute equal to 454 grams. Oops, 454 grams. Molar mass of sugar is 342 grams. I think that is 1.33? Okay, thank you. 1.33 moles. So the molality is 1.33 moles of sugar over 0.5 kilograms of water is 2.65 molal.
What is?
Okay, so the change in freezing point temperature is equal to 1.86 times 2.65 times 1, and that is equal to 1.35 degrees C. That's how much the freezing point will change. The freezing point of the solution of sugar and water is equal to the freezing point of the pure minus the change, the freezing point depression. So,
Yeah, that doesn't make sense.
I got 4.95.
Yeah, I got 4.
oh, maybe I did too. Oh, you know what that other one is? The boiling point. Yeah, it's the boiling point one. Sorry, looked at the wrong place. So when you multiply this stuff together, it's 4.94. 4.94. Alrighty, so 0 minus 4.94 is equal to negative 4.94 degrees C. What is this number? The freezing point of the solution. Now I just gave you the answer away to the boiling point, but do it to yourself anyhow.
Yeah, what was it?
Yeah, I wrote over it, you can't even tell. Do it yourself.
4.85.
No.
1.3.
Look at after we
Yeah, because I read it like 6 times before I came home.
What are we doing with the boiling point?
To do the boiling point, please. I do need to give you one bit of information. What bit of information do you need from me? Nope.
Molal.
KB. KB is equal to 0.51 degrees C per molal.
Wait for 5.1.
0.51. That's a good idea.
It's like a mole out,
A
right?
stand for?
The mole freezing point depression constant.
What is the KB?
Oh my God.
Alright.
He asked me the boiling point.
No, I asked what the question was, because I didn't see it said boiling point.
Has the molality changed?
Nope.
Has the Van Hoff factor changed?
Yep.
No, it hasn't.
Oh.
One 1.35 degrees C. Who's surprised by that number?
That's what I got.
Good. That works out well for us. Okay, ladies and gentlemen, here are free answers for the lab for tomorrow.
On the pre-lab?
For the lab.
Oh,
Exactly what you need to do in order to get the right answer on the lab. Okay. So, tomorrow, you're going to be using a freezing point depression of a molecular solvent, solute, I'm sorry. You're going to take a molecular solute, you don't know what it is. You're going to take 2 grams of it, and you're going to put it in a known quantity of solvent, which happens to be water, and you are going to determine the temperature at which it freezes. You know, and it will measure the freezing temperature of water. And so you will experimentally determine the difference in freezing temperature between the pure water and your solution. I'm going to give you, in tomorrow's case, it will be the KF. You're going to know the Van Hoff factor for this molecule will be,
1.
and you'll solve for molality, keeping in mind that molality is in moles of solute over 1 kilogram of solvent. You are going to figure out how many kilograms of solvent you use. You will multiply that times the kilograms of solvent you used. And when these two values cancel, you will end up with moles of solute. The molar mass is always the amount of solute that you used in your experiment divided by the moles of solute. You've just figured out the moles of solute. You're going to be aware of how many grams of solute you put in your test tube. And that's going to give you the molar mass of your molecular solid, or solute. What?
That's pretty good.
It is kind of nifty. It works out really well, and I don't have to bury the result. So here's the math behind it, or something similar. This is going to be a boiling point elevation. The process is similar. A solution was prepared by dissolving 18 grams of glucose in 150 grams of water. The resulting solution was found to have a boiling point of 100.34 degrees C. Calculate the molar mass of glucose. Glucose is a molecular solid that's present as individual molecules in solution. Kb is equal to 0.51 C over molar. All right, so I think I want to remind myself that this is the solute. This is the solvent. I know that the freezing point of the solution, the boiling point of the solution is equal to 100.34 degrees C. The boiling point of the pure is 100 degrees Celsius. The change in temperature due to the addition of the non-volatile solute is 0.34 degrees C. I is 1, and Kb is 0.51 degrees C per mole. I think by using what I see that I have given in the problem, I can solve for molality. My molality is equal to anybody else get 0.67? 0.67 moles per kilogram, which is the definition of molality. I'm going to multiply that by the number of kilograms of solvent that I used, which is
0.0.
These will cancel, and the number of moles of
0.1.
solute is 0.1. That's handy. 0.1 mole of solute. The molar mass of our non-volatile solute is equal to the grams used over the moles calculated. The grams used is 18. The moles calculated, 0.1. Our molar mass is 180 grams per mole, which turns out is the right answer.
Okay, what you do with the molality?
I took the molality and I broke it down into its parts. The term molal equals the moles of solute per 1 kilogram of solvent. To that, I multiplied the kilograms of solvent that we used, causing these two to cancel out. And I'm left with the only unit moles, which is what I'm looking for.
Where did you get 0.67?
0.67 was when I solved for molality right there. Okay, I want to do some more skipping around, please. We'll come back to these problems in a moment. I would like to talk about osmotic pressure. That's the last colligative property that we're going to talk about. And it's who's taking note? Bio2. Okay, this is a big, big topic in Bio2. All right, let's take a closer look at our picture. All right, osmotic pressure is formed when you take a semi-permeable membrane. In this case, semi-permeable means well, in all cases, semi-permeable means some things can pass through and some cannot. This semi-permeable membrane allows the solvent particles, water, to flow through, but not the solute particles to flow through. Therefore, on this side of this tube, there's a very high concentration of solute particles, and on this side of the tube, there's a lesser concentration of solute particles. Things in nature always go from high to low. High solvent particles, low solvent particles. Thank you. So what's going to happen is the solvent particles will migrate across the semi-permeable membrane and actually cause this to go up the tube. Osmotic pressure is the amount of pressure needed to counteract that forward motion. That's what osmotic pressure is. Okay. It is a colligative property that is bound by this formula. The osmotic pressure, which must be an ATM, please circle that because you're going to get it wrong, is equal to the molarity of the solution times the gas law constant that we usually use this number, lat momolka, times the temperature in Kelvin, times the Van't Hoff factor of the solute. Just do the math.
So would they provide us with conversion factors if you need to change it from a different?
Probably not. You should be pretty good at knowing that 760 torr is the same as 1 atmosphere, and you should know 760 millimeter of mercury. Anything other than that, maybe even on your green sheet. They might be nice to you, they might not be nice to you. Okay, this is simple math. Fill in the solve for the missing variable. Okay.